Alright, we are talking about chapter 8, which is binary numbers or the binary system. And it's really a special case of the general base numbers where the base is 2. And that's really all it is. But because of its importance in technology, we give it a separate chapter to give it a little bit more attention. So one thing to notice is that just like how I broke a number into pieces based on powers of 5, I can do the same with powers of 2. For example, we're just going to do this by example. And I'm looking at exercise 8.1. The number 1 is 45. I can break this up and say, well, what is the highest power of 2 that can go in here? Well, what are the powers of 2? Powers of 2 are 1, 2, 4, 8, 16, 32. 32 can still fit, but the next one is 64, which is too big. So I can say, well, this is 32. My pencil doesn't really work well. Hold on. This is 32 plus, how much is left? Well, 45 minus 32, and I have 13 left. Then I have my 32 and I want to split the 13 into smaller powers of 2. The biggest one I can use is an 8. How much is left? 5. Then I can split the 5 into smaller pieces. It's going to be a 4 plus 1. So any number can be split up into the sum of some powers of 2. Now, to be a little bit more precise here, we are going to say 2 to the 5 and not skip any. 2 to the 4 is 16, but it's not there. So I need to say I have one group of 32, 2 to the 5. Let's make a little bit of space here for that adjustment, plus 0 groups of 2 to the 4 because there aren't any. I do want an 8, and an 8 is 2 cubed. I do like 4. I need to use a 4. Then I don't have any 2's. I skip 2. So I have 0 2's, which is 2 to the 1. And I have 1 left, or 1 group of 2 to the 0. So all of them are powers of 2. Some are there and some are not. And because I have only my base is 2, the only numbers that can be here are 0 or 1. So we then say 45 has a representation in binary. Same as before, these are the digits. So 1, 0, 1, 1, 0, 1. And we should write a base 2 there, but if we are working in our binary numbers, and it's clear from the context, you are okay to drop that. But if you have any doubt and there are other numbers floating around, then you should say, no, I'm working in binary. Otherwise, this could be read, if I don't have that, this could be read as 101,101. So I need that 2 there. But you'll see it sometimes left out in the question when they say these are binary numbers. So that's 1. Let's do another example with a bigger number. Now I have 237. And we can also use our table like we've done before, especially when the numbers get bigger and I need to keep track of all my powers of 2. So I can't remember exactly how we did it. It's totally up to you how you want to adjust it. We can call this digit, I think it was, and then what is the power of 2 that I'm using, and then how much do I have left. So right now I have 237 left. what is the largest power of 2 that I can fit in there? Well, I need to know my powers of 2. So let's write it over here, and we can refer to that. Powers of 2. 2 to the 0, 2 to the 1, 2, 3, 4, 5, 6, 7, 8, and we'll see how many we need. 2 to the 0 is just 1. Why did I write? I said 0, so I wrote 0. 1. 2 to the 1 is 2, then 4, then 8, 16, 32, 64, 128, 256. I can keep going if I want to. 512. 2 to the 10 is 1024. And you don't have to memorize them all, although the first group here up to 1024, it's handy to remember. And that's as far as I've bothered to memorize it. Anything bigger, and I'll use my calculator. So the biggest one I can fit in into 237 is 2 to the 7. And I'm going to do it only once. Now I want to list all of them, even when it can't fit in, because it's going to be a digit, and that place is important. So 2 to the 7 is 128. So I take that away, and I have 109. Then I am going to look at 2 to the 6, 64, and 64 does fit in, but only once. If I can fit in more than one, I did something wrong. These digits will only be ones and zeros. So now 2 to the 6 is 64, so I take that away from 109, and I get 45. Next power of 2 is 2 to the 5. I can fit it in, it's 32. So I fit in 1. Let me extend my lines here. I've used 32. How much do I have left? Well, the difference is 13. The next power is 2 to the 4, which is 16. That's too big, so I can't fit any of that in, and I still have 13 left. Then 2 cubed, which is 8. 8 I can fit in, only 1. And then I have 5 left over. 2 squared is the next one. 4, I can fit a 4 in. One of them. I've used 4, I have 1 left. Can't skip 2 to the 1, otherwise my places won't be correct. And 2 is too big, so I won't use any of them. Still have a 1 left for my last one, which I will use, and I'm done. So that tells me here that the binary representation, or the binary expansion based on powers of 2 is 1 times that, plus 1 times that, plus 1 times that, plus 0 times that, and so on and so on. You don't have to write all of that down. It's going to go from big to small, so it'll be 1, that one, then that one, then that one, then 0, 1, 1, 0, 1, 1, 1, 0, 1. And I should say here base 2. So as the numbers get bigger, 237 is not even that big. But if the base is small, my options for each place, for each digit, is really limited, and the effect is that the length of the number gets really, really big. We'll look at number 3 just to emphasize that, but it does get a little tedious as I move to bigger and bigger numbers. So we'll just do 1 that's a little bigger just to see. Now I have my powers of 2 here. Maybe we'll shift it a little like this. I have my powers of 2 there, my cheat sheet, though you can memorize them if you want to. And it's good to memorize up to that, but now I see that, ooh, what's 2 to the 11 going to be? I don't necessarily know, or, well, I do know, but I don't necessarily need to know. If I multiply that by 2, clearly I'm going to be over 1589, and I'm going to have 248. So my first power that I'm going to use is 2 to the 10. We might as well extend these lines all the way down because this is going to be a long one. Left column here, and I have my digit, or how many I use, how many I can fit in, which in this case is always going to be a 0 and a 1. So I have my 1589 left. Now 2 to the 10 is 1024. I can fit it in once. How many do I have left? Well, it's really 589 minus 24, which is 565. Try and squeeze them in here a little bit because we are going to go down all the way. Once we've started, we can't skip any of them anymore. So I'm going to go all the way down. Seems like we have space for that. Now 2 to the 9 is 512. Oh, it fits, it fits. Now what's the difference? How much do I have left? Well, 65 minus 12 is 53. Now 2 to the 8 is too big. Still 53 left. 2 to the 7 is too big. Still 53 left. 2 to the 6 is too big. Getting closer, but too big. Still 53 left. 2 to the 5, that is good enough to fit. 32. So I'm going to fit in one of those. How much do I have left? Well, 53 minus 32. And of course, feel free to pause if it's going too fast for you, if you want to think before you just hear it, or whatever you need to do. The beauty of a video is you can go back and forth as you want to. How much do I have left? 53 minus 32 is 21. 2 to the 4 is 16. Oh yeah, that'll fit. And I have 5 left. Now 2 to the 3 is 8. That's too big. I only have 5. So I still have 5. 2 to the 4 is 4. Yep, can fit one in, one left. But 2 is too big, and I'll use 1 there. So this then has binary representation, top to bottom, 1 1 0 0 0 1 1 0 1 0 1. And because the base is small, my length of my number is so much bigger. So I'll leave this cheat sheet here as we move on to our next example, just as you can expect, converting the other way. So now we're looking at exercise 8.2. So I have my binary number, and number 1, 1 1 0 1. Now that's base 2. So that means my powers go from right to left, 0 1 2 3. So I can maybe have a little note there. My highest power is 3. So it's 1 group of 2 to the 3 plus 1, the next one, group of 2 squared, plus 0 groups of 2 to the 1 plus 1 group of 2 to the 0. Now that's 8 plus, I can write it down, 8 plus 4 plus, not that one, plus 1. So that's 13. So that conversion is maybe easier since I don't have the whole table and fitting in stuff to do. Number 2, make sure I write this down, 1 1 0 1 0 1, base 2. So I have my powers of 2 from right to left, 0 1 2 3 4, and 5 is the highest one. Now you can do everything right to left, but for some reason we don't really do that. So I have 1 group of 2 to the 5, another 1 group of 2 to the 4, no 2 cubes, 1 2 squared, that one, 0 2 to the 1s, and a 2 to the 0. So that gives me 32. 16, and it definitely helps if you memorize these smaller powers of 2, 4 and 1. A little addition, never hurt anyone. That is a 48, 52, 53. And there you go. one more. One more, we can do it. We just have to make sure we write the digits down correctly. 1, 1, 0, 1, 0, 1, 0. So counting from right to left, the places essentially correspond to the position of these digits correspond to the powers of 2. 0, 1, 2, 3, 4, 5, and 6. A little bigger than the previous one. So I have 1 group of 2 to the 6 plus 1 group of 2 to the 5, then 0, 2 to the 4s, 1, 2 cubed. Now where are we now? 6, 5, 4, 3, 2. 0, 2 squared. 6, 5, 4, 3, 2, 1, 0. And 1, 2 to the 1, 0. No, you can't see this, I'm sorry. 0, 2 to the 0. So then I have 64, 32, skip that one, 8, skip, and a 2. Little addition, 64 plus 32 is 96. 96 is 104, 106. And we're done. So it's very similar to the previous base numbers. Just base 2, my options are very limited. Now, the reason why binary numbers are so important is that all computers are essentially built on binary numbers. In that you, on your circuit board, you send electrical signals. They can either be on, which would correspond to a 1, or off, which would correspond to a 0. So by having a lot of little switches on, let's write it like this, on or off, if I can imagine a switch like that, off and on, and maybe another off. Now these are signals that you can interrupt, not actual switches, but just to have an indication. I can have a long binary number, and everything has to be done in binary because only a 1 or a 0 can be stored and used as a place value. So everything has to be done in the binary system. Now with increased memory, these numbers can be really, really long. Whether I can write them that long, whether I can or not, the computer doesn't have that limitation. So the numbers can be really big and the quantity is really large, but everything has to be done in binary. So the example in the book uses light bulbs instead of little signals, but either a signal is on or off, regardless of exactly how you look at it. So with the light bulbs being on and off, just like these, on and off, we can represent quantities and work with them. Sort of design a machine to perform these calculations by understanding the binary numbers. So we have a little example 8.3 for that. Write the binary numbers suggested by each of the following, then convert the resulting binary numbers into their decimal equivalent. So number 1, I have on, and off. So on, and off will be my binary number. So that will correspond to, well, 0, 1, 2. 1 group of 2 squared, 1, 2 to the 1, and 0, 2 to the 0. So my number therefore is a 4 plus a 2, so that, and the light bulbs can represent number 6, and the machine can use that number 6 in calculations. It's not dependent on our thinking anymore. It can perform the calculations in a systematic way by just flashing lights on and off. So it's a fascinating concept if you think about who came up with these ideas first, that calculations can be automated. Now, these days, we just use it without even realizing the progress and the technology that works behind it. We take it for granted for sure. As the number 2, I have on, off, on, on. On, off, on. What is the number represented by those light bulbs? Well, 0, 1, 2, 3, 4. So 2 to the 4 is the biggest. So I have one group of 2 to the 4 plus 0 groups of 2 cubed, one group of 2 squared, one group of 2 to the 1, one group of 2 to the 0. So I have a 16, a 4, a 2, and a 1. So that is 23. Let's do one more before we wrap it up. We have our light bulbs on, off, off, on, on. On, off, on. Still need to make these too big to get the point. So we have 0, 1, 2, 3, 4, 5. So 2 to the 5 will be the biggest one, and one of them. Then a 2 to the 4. Then no 2 cubes, no 2 squareds, a 2 to the 1, and a 2 to the 0. So I have 32, 16, 2 and 1. 2 and 1. So it's 48 and 51. So you can research binary numbers a little more to see how much innovation really went into that, historically speaking, and how it really revolutionized our society.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.